Hey, hi everyone. Welcome. It's a great pleasure to start this second season of Global Non-Commutative Geometry Seminar. So we have lots of other talks lined up in coming weeks. Please check the website, register, and you will receive announcements regularly. Now, to today's talk, it's my great pleasure and distinct honor to introduce our special speaker, Alain, who doesn't need any introduction, thankfully. So Alain will talk on the notion of space, as you can see. Alain, please.
Okay, thank you, Masoud. I'm very grateful to the organizers for asking me, to deliver this talk on the notion of space. And I mean, what I have chosen to do is, if you want to use two different paradigms for understanding what is a space. So the first paradigm is a very classical one. It is the one of algebraic geometry. And I mean, in a broad sense, I will consider it as follows. So there is a kind of a base space, if you want, which is a topos in the sense of Grothendieck. And this kind of base, if you want, which is a generalization of a topological space, has a structure, and this structure is given by a sheaf. So the notion of sheaf, of course, makes sense almost by definition. And this sheaf will be of algebraic nature. So I mean, I won't, of course, go into any detail at this point, but I mean, this is a broad version, if you want, of the framework of algebraic geometry. Of course, I include their manifolds, I mean, and so on and so forth. And I mean, and this framework, I mean, it is typically something which I would describe as being local, as being classical. And it's classical in the sense that, it doesn't involve, it doesn't ascribe a special role to complex numbers. Now, the second framework is quite different. It is of quantum nature. And I mean, the place where everything takes place is Hilbert space. I mean, the Hilbert space, which is the only, if you want, infinite dimensional with, of course, countable basis, Hilbert space. And I mean, it really is the paradigm which, as I will try to explain, has, of course, fundamental importance in non-commutative geometry in the sense that the algebra, which is involved and which is concretely represented in Hilbert space, doesn't need to be commutative. And I mean, in the sense also that all the metric relations are encoded by another operator in the same Hilbert space. So they share the same sort of stage, if you want, which is this Hilbert space, and which plays a role of the Dirac operator. Of course, we shall see that in great detail, but we shall see that in great detail, if you want, not abstractly. I don't want to talk abstractly. I want to talk about two very concrete examples. And I mean, these examples will be the following. They will be space-time and the primes. So, I mean, when you talk about geometry, you can imagine all sorts of spaces, but there are spaces which you cannot dispense with. I mean, you cannot dispense with discussing space-time. What is the simplest manner that we understand space-time at this point? I mean, in a very simple manner, there is a topological space, okay, which is the space-time. And this topological space has an additional structure, which is given by the G minus. Okay. Now, these things are understood from Riemann and then from Einstein to be of Minkowski type. So there are 3 pluses and 1 minus. But I mean, for the understanding and due to a lot of thinking of physicists and so on, I mean, it's simpler at the first shot to move by what one calls a Wick rotation in the situation where you have 4 plus signs. This move looks a little bit artificial if you don't know quantum field theory, but when you are doing quantum field theory, you will find out that even to define what are the propagators and so on and so forth, to define the Feynman graphs and so on, you have to move to Euclidean. Namely, you have to do this Wick rotation. The trouble, if you want, with this simple form of things is that it accounts for gravity, but gravity is not the only force of nature. There are three other forces, and they are not accounted by this simple paradigm. Now, for the primes, there is also a very simple, if you want, down-to-earth paradigm for the primes, which is to think of the primes as being the prime ideas of something that one calls a spec Z, if you want, which is to look at the prime ideals in the ring Z of integers and endow this, which is of course a Grothendieck topos in a very trivial way, to endow this with a sheaf, which is obtained by localizing the ring at various primes. When you do that well, you obtain something which is reasonable. But if you push things a little bit, you find out that it's not as nice as it looks. And there are two reasons why it's not as nice as it looks. I mean, the first reason is that when you take Z and you tensor by Z over the smallest rings that you know, which is Z itself, where you find Z. And I mean, this doesn't fit at all with the idea that you are really considering, affine functions on an affine variety. And because normally when you cross it, I mean, you get something which is more interesting, which is a surface. So this is the first issue. And the second issue is that really, I mean, it's an affine situation. It's not corresponding to a compact stuff. And if you want to compactify it, well, there is a known compactification, which is the Arakelov compactification. But when you look at the structure sheaf over spec Z, which is a subsheaf of the constant sheaf with the stock equal to the rational numbers, then, I mean, if you use standard techniques, you cannot extend this sheaf to the Arakelov compactification. So you see from the start that I wouldn't call it naive, but I mean, this kind of straightforward, if you want, idea doesn't really work. And in fact, what happens is that when you look at the universe at very distant parts of the universe, what the universe has chosen to communicate with are spectra. And these spectra, I mean, they contain an enormous information, which if you wouldn't look closely, you would miss totally. The reason is that they have something like a barcode, this spectra. So when you look at this spectra, which you get from the light coming from the sun or from very distant galaxies and so on, or from the universe, from parts which look empty. In fact, what you find out is that there are absorption lines in this spectra. And these absorption lines, when you look at them very, very carefully, what you find out is that they give you an enormous information about the chemical content. Why? Because these barcodes, there is a specific signature for each chemical. So they give you information, for instance, about the redshift, which is an amazing fact because it tells you that these galaxies are shooting off. And as we shall see very shortly, they give a much more precious information, which is the information about quantum mechanics. Now, the set of primes, similarly, it looks a little bit, when you look at it, you spell out the primes 2, 3, 5, 7, 11, 13, 17, 19. Okay, I mean, it's but in fact, they do manifest themselves also spectrally. And this is through the set of zeros of the Riemann zeta function, which when you look at them, you will find out that, it really looks like one of these physical spectra. Now, the reason why I said that, these spectra, they contain an amazing information is the following. It was discovered by Ritz and Rydberg long time ago, that in fact, the spectral rays that you see, when you view them, not in wavelengths, but in frequencies. So what you do, you plug in the frequencies and you plug in the corresponding spectral rays. Now, what you find out is that there is a natural way to label them by two indices, not by one index. And when you label them by two indices, what you find is that for things which are labeled like ij and things which are labeled by j and k, where the j is in common to the two, then the frequencies add up. So it's not a group, but it's something which has a partial law of composition, which is given like that. Now, this fact looks a little bit strange. I mean, when you see this at first, but the guy who completely deciphered it is Heisenberg. So Heisenberg, I mean, what he found, if you want, which is absolutely amazing because he found it for physical reasons. His reasoning, in fact, amazed a friend of his. I mean, he was with Dirac, in fact, when he was making his studies, and Dirac was amazed by the discovery of Heisenberg. So Heisenberg and all these people, they were looking at spectral rays, they were looking at understanding spectra and so on. And what Heisenberg found is that, in fact, the key was in the Ritz-Rydberg combination principle. And what he did, he said, okay, well, I don't have a group. If I had a group, he was talking about action angle variables in which you have a Fourier transform. So he was saying, normally, if I was doing classical mechanics, I would have a group, the group of frequencies. It's not a group. But I can do the same transformation as I do with the action angle variables. And what do I get? Well, he computed what he gets. He used the Ritz-Rydberg combination to define a product. Okay, in modern language, we would say that he was defining the groupoid algebra. But in this case, for a simple chemical, which has, if you want, transitions going from any to any, what he found are matrices. And this was absolutely amazing because he had no idea that matrices were known to mathematicians. And this was found later, by Born and Jordan. And and this opened up a complete world. And in the hands, of course, of Schrödinger, the spectra were completely deciphered. They were understood from spectral operators in Hilbert space, which had been defined before by mathematicians and called spectra. And in the hands of von Neumann, and the things developed considerably. Von Neumann and Murray, they considered the subsystems. They understood that everything was taking place in Hilbert space, that Hilbert space was a correct stage for quantum mechanics. And so what happened is that, to me, if you want, this discovery of Heisenberg is really the birthplace of non-commutative geometry. It's really the place where it was born, in the sense that he found that when you consider a microscopic system, and if you look at what people call the phase space of this system, then this phase space, you cannot take it to be commutative. It's a non-commutative space. And then, okay, when I started working, I worked on factors. And after my work on factors, I found that there were ubiquitous, non-commutative space were ubiquitous because of foliations. And that foliations were giving so many examples of non-commutative spaces that one should develop geometry for them. And what I found out after many years is that when you try to develop geometry for spaces whose coordinates do not commute, it leads you to a spectral version of geometry, to a purely spectral version of geometry. Now, this spectral version of geometry, I had no idea whatsoever that it would apply to space-time. I mean, it was intended to understand non-commutative space. It's not space-time in any way. So at this point, I think I will pass the scene to my alter ego. And so I will stop sharing my screen and now go.
And this spectral point of view, in fact, I mean, it's quite amazing that, Riemann had in his inaugural talk on geometry, had, if you want, the honesty of saying that nobody can say that his paradigm of geometry would continue to hold at very, very small distances. And the reason that he had in mind was that when you go to very small distances, then the notion of a light ray or the notion of a solid body, which he was using in his own conception of geometry, no longer makes sense. And he wrote some amazing phrase, which is that in fact, what he says, that the metric relations, in fact, should come from the binding forces, which sort of hold things together. And what we shall see very shortly is that the spectral paradigm, which I will explain now, in fact, has exactly this power, that it embodies not only the gravitational force, but it embodies all the other forces that we know so far. Okay, and so how is this done? Well, this is done by somehow, extracting the square root of the square of the line element as defined by Riemann, and this extraction of the square root is operator theoretic, and it goes back, in fact, to Hamilton. It uses the Clifford algebra, and it was concretely done by Dirac in an amazing vision. And I mean, the way it's done is that, when you want to take a square root of the sum of squares, this is not so easy, except if you use Clifford matrices, because they anti-commute, so that when you raise a sum of them to the square, the cross terms disappear, and you get a sum of squares. And it turns out that in the spectral paradigm, which is, fundamentally in noncommutative geometry, what happens is that it is the Dirac propagator, or if you want, it is inverse of the Dirac operator, which becomes a line element. And this allows you to work, but to work already in a quantum mechanical environment, because you are working in Hilbert space. You have an operator, and the way you measure distances is no longer by making, an arc, or taking an arc and taking its minimal length between 2 points. No, it's by sending a wave, and but this wave has a kind of bound on its frequency, because and the specific condition is that the commutator of the function with the Dirac operator is bounded by 1 and no. And in that way, you measure also the geodesic distance. But you have a formula for distances which is much more adaptable, in the sense that it doesn't require space to be arcwise connected and so on and so forth. And it works in many, many situations in which the other paradigm wouldn't work. And it gives you the freedom to, if you want to incorporate fine tuning, fine details of the space that the previous formalism, with its limitation to the continuum, wouldn't allow you to do. So in fact, what happens is that there is, of course, a dictionary. So there is a tool from classical to quantum, which is very, very fundamental, which, in part goes back to, I would say, von Neumann, and which says, if you want, that, okay, the notion of a real variable, which gets replaced by Selfadjoint Pareto. They have all the right properties. The Selfadjoint Pareto has a spectrum, which is like the set of values of the variable. One of the most amazing facts of Hilbert space operators, which I remember I was so struck by when I was a sort of a beginning mathematician, is the fact that when you take a Selfadjoint operator, you can take any measurable function of this Selfadjoint operator, and it will still be a Selfadjoint operator. This is kind of totally mind-blowing. And it's due, of course, to the spectral decomposition, but it's an amazing fact. And you can apply to a Selfadjoint operator a function which is defined differently on different intervals, and it will still make sense. So this is the notion of a real variable. There is a notion of a complex variable, and typically, the great genius of Dirac was to use this commutation relation that as a commutator of A and A star is equal to 1, and that implies that the modulus square of A, which is A star, is quantized. It's an integer. Then there are the values of the variable, which, as I said, just form the spectrum of the operator, and they can be discrete and continuum. And this is an amazing fact, because if you would take the usual framework of variables, and if you had just one discrete variable, the set X would be countable, and it wouldn't allow for continuous variables. Whereas in Hilbert space, the two coexist, but they don't commute. This is the only thing that you have to remember. Okay, so then there is room for infinitesimal variables, and there is an amusing fact, I mean, quite revealing actually, which is that Newton, when he wrote, when he was thinking about infinitesimals, was never thinking about a number like Leibniz. He was thinking about a variable. And what is amazing is that if you look in the writings of Newton, you will find out that he had a definition of an infinitesimal variable, which when you use a dictionary from the classical to the quantum, exactly characterizes what we call compact operators in Hilbert space. Now, these compact operators have the right algebraic properties. They form an ideal, two-sided ideal. They, if you want, they, of course, this means that you can add them and you still have an infinitesimal, but they also have an order. So you have a notion of infinitesimal of order alpha. This is saying essentially that when you take the characteristic value of the operator, characteristic values, which are the eigenvalues of the absolute value of the operator, then they decay like a specific power of n. The nth characteristic value is of the order of n to the power minus alpha. There is a notion of differential. I mean, the notion of differential is obtained by taking a commutator, because it's an operator of square one. And there is a notion of differential form. This notion of differential form is at the root of the discovery which I made in 1980 and 1981 of cyclic homology. Because you can develop a calculus which I call the quantized calculus, and which gives you immediately the right notion. But there is much more. So there is the fact that the line element now is, if you want, the Dirac propagator or the propagator for fermions, and it embodies the geometry. And there is a fact that, as I said, I mean, you can compute the distance as you were doing before, but the most refined and the most, how to say, original of these new ingredients is the integration. And the integration uses an idea which goes back to Jacques Dixmier in the 60s. He discovered, a trace which is not the ordinary trace on operators. And so I had the chance to have lunch once with him at Bure-sur-Yvette. And it was amazing because I was looking exactly for what he had. And what he has is, if you want, a way to pick the logarithmic divergency of the trace of an infinitesimal of order 1. So if I have an infinitesimal of order 1, its eigenvalues will be like 1 over n. So if I try to sum them, they diverge because, it's harmonic cells. So, they diverge. However, it turns out that Dixmier had found a way using amenability of the solvable group to pick the coefficient of the logarithmic divergency. And in such a way that you get a trace, you get something which is additive and which is a trace. And so, this opened up a complete world because what it meant is that one could give a meaning to the integral independently of the measure. If you want, in this quantized calculus, an amazing fact is that you have the notion of infinitesimal and you have the notion of integral. And normally when you do measure theory, you get a whole package and you get integral of f of x d mu of x. And integral or d mu of x don't really separate. They are in the same box. But here it's not at all the same. Here is the notion of integral, which is obtained by taking the coefficient of the logarithmic divergency, is absolute. And in fact, I believe that most of the integrals that we know, in fact, are special cases of this. You have to think a bit about it, but for instance, the integration over a Riemannian manifold for the volume is exactly the integration in this sense of the Dixmier trace of the right power of the line element. The power n, where n is dimension. Okay, so these are the tools. And one more very tantalizing fact, okay, which of course would need a lot more work, is that because of the quantum field theory, and because the line element which defines the geometry is defined as an operator, it turns out that it gives room for quantum corrections. I mean, one knows in physics that the propagator of fermions gets dressed by the quantum field theory corrections, and it gets dressed, if you want, by a formal power series in powers of h bar, in powers of the Planck constant. So what this means is that if we understand geometry from this spectral point of view, then I mean it is the correct receptacle in order to take it into account the dressing from quantum field theory. And of course, this is what happens in reality, because in reality we cannot turn off the quantum field theory. It is there. So this means that if we really understand that our measurements of distances are using this secretly, because for instance you have the electronic microscope or such things, then in fact the geometry we are talking about is already quantum. Now, of course, this is amazingly suitable for non-competitive geometry. Why? Because the paradigm, which is given by spectral geometry, which is given by an algebra, which is represented concretely in Hilbert space. So the algebra represents the space in a naive way. And this self-adjoint Pareto, which is the inverse of the line element, well, the algebra doesn't need to be commutative. And there are thousands of examples, okay, which, if you want, show that, I mean, taking the algebra to be non-commutative is a great benefit, in fact. And the simplest way of understanding this is to modify the algebra in a very trivial manner by taking matrices over the algebra. I mean, when people do, for instance, case theory and so on, they know very well that even if you start with a commutative algebra, and when you want to understand bundles and so on, you better replace the algebra by matrices over it, and by matrices over it. So that's what you do. And what you find out is that if you do that, well, it turns out that the group of diffeomorphisms becomes more subtle. Why? Because normally when you take the algebra of smooth functions on a manifold, the group of diffeomorphism is simply the group of automorphisms of this algebra. This is the fact. But now if you replace the algebra by n-by-n matrices of functions, if you want, of elements of the algebra, then what turns out to be the case is that because the algebra becomes non-commutative, it has, among the automorphisms, it has rather trivial ones, which are the inner automorphisms, and they form a normal subgroup. So what happens of the group of automorphisms? So, and what happens is that if you want, you have an extension of the group of diffeomorphisms, which is still there as a quotient of automorphisms by the inner automorphisms, but it's an extension by what physicists call the gauge group of second kind. So it introduces, almost for free, the gauge transformations of the second kind in that example for a group SUN. And what we did with my collaborator Ali Shamseddin a long time ago, we found out that if you write what replaces gravity, but in a spectral manner, which we call the spectral action, which is just, judging the line element, I mean, roughly, I mean, counting how many eigenvalues of the line element are larger than the Planck length. I mean, this is very rough. So if you do that, then you will obtain not only the Einstein action, which appears naturally, but you will also obtain the Yang-Mills action for these additional fields which come from the inner automorphisms, which come, if you want, from the inner part of the metric. So this was very encouraging, long time ago. And I mean, this was back in the 1996, and then a lot of things happened, and I want to be extremely concise about this, because somehow, if you want, the main difficulty that remained was to understand what type of non-commutativity one should put in the algebra, so that we recover not only the Young-Mills coupled to the gravitation, but the full standard model with all its complicated things like the seesaw mechanism, like the V minus A of Feynman and Gell-Mann, like the Higgs field, of course, and so on and so forth. And it turned out that we found with Shamseddin and Mukhanov, we found a solution to this problem, and we found a solution purely motivated by geometry. So the solution came about as follows. You see, the Dirac operator has a great impact that somehow it is a concise way to assemble together all the momenta. Instead of giving the momenta P0, P1, P2, P3, you assemble them using Clifford matrices, and you have a single entity. I mean, this is in a way the generalization of the idea that the complex number is a nice way to put together two real numbers, but in a single entity. So here, if you want, the Dirac operator was sort of encapsulating all the momenta into a single entity. Now, after a lot of thinking, a lot of time, and so on, we finally found with Ali Shamseddin and Slava Mukhanov that there was a similar way that one could encapsulate the coordinates, if you want the position variables. There was a way to encapsulate them, but of course, in order to encapsulate them, you also need some kind of Clifford matrices. And from purely geometric considerations of maps to the fourth sphere and all that we thought about and all that, we found out that there was an equation that would then couple together the Dirac operator, which puts together all momenta, with a certain operator that would encapsulate together all the coordinates. And this equation is an either higher form of the Eisenberg commutation relation. You know, Eisenberg was there was this great relation which is P commutator Q is equal to IH bar or something like that. And what we found with Shamseddin and Mukhanov is that there is a way in dimension n to write an equation which involves n times the d, the inverse of the line element, and which involves this operator z, which actually encapsulates all coordinates together. And this equation will be the kind of the roof of the whole building, because it will prevent it from collapsing. Because if you have an equation like that, for instance, you cannot represent it in finite dimensional space, and it will sort of, its irreducible representations will yield you geometries. And where we were totally stunned was that, you know, before with Ali, I mean, we had worked from bottom up. So we had started by looking which algebra was working and so on. And after a long, long time, we had found a certain specific algebra, which was 2x2 matrices of quaternions and 4x4 matrices of complex numbers. And that was doing the right job. But the real, intense pleasure of understanding was when we found with Ali and Mukhanov that the Clifford algebra that we need in order to make this geometry, this geometric pairing, is exactly, in fact, the Clifford algebra which is coming from 5 gamma matrices and which is either with a plus or a minus, and they give exactly the algebra that we had found from our bottom-up working. And it was all the more amazing because, I mean, when you look at these two algebras, they don't have the same real dimension. So it seemed impossible to find a good conceptual explanation for them. I mean, C plus, it's a 2x2 matrix of quaternions. So, I mean, the dimension is 4 times 4, which is 16, but the other one has dimension 32. So, but what happens, I mean, with the Clifford algebra is that, in fact, you need an irreducible representation, and normally the C plus is M2 of H plus M2 of H, but of course one of them is not needed when you take an irreducible representation. So this was the explanation. And the second, I would say, breakthrough that we did was that then we found that if you take these two, then it turns out that you can encode all spin-4 geometries, namely all compact spin manifolds of dimension 4. We are working in the Euclidean framework by taking irreducible representations. And I mean, this came about from a theorem which was quite difficult to prove. In fact, I got even some help from Simon Donaldson, and which in fact gave the condition that the square of the second Stifel-Whitney class would have to vanish. But I mean, this is the case when you take a spin manifold. So in fact, what happens is that first of all, when you apply this either an irreducible representation of this higher Eisenberg relation, the volume is quantized. And second of all, if you have a 4-spin manifold and its volume is quantized and larger than 5 as an integer, then you can find it as an irreducible representation of these relations. And I mean, this solved many questions. One of them was the fact that in the spectral action, normally you would have a huge cosmological constant, but because the volume is now quantized, this problem disappears. So, I mean, this is where we stood. I mean, there were several important papers. So the paper with Ali Shamseddin and Slava Mukhanov is called Geometry and the Quantum Basics. And another new development that we made since then was to understand that the spectral action was in fact an entropy. It's an entropy when you consider second quantized fermions. You find out that it's an entropy. So this is, of course, a contribution, very important contribution of Walter van Zijl-Kom, who collaborated with us, and Walter also had, unveiled many properties of the models that we had by comparing it with Partition models. And in fact, I mean, there is a recent work of Walter and of his student and Dylan. What they have done the great discovery, which is that, in fact, one can follow up the spectral action under a normalization. That was, something which was very much missing in the spectral action formalism. And I mean, to summarize what I have said, there is an interview which I did in 2016, which has just appeared now in a book which is called The Conversation on Quantum Gravity by Cambridge University Press. I mean, I'm probably I'm a mathematician that was interrogated. Not that I know much about quantum gravity, but because of the potential links, if you want, of noncommutative geometry with quantum gravity. Okay, so this will be so far for the space-time. And the next thing will be to now look with, some concentration to what I call a mysterious spectrum, and we shall see what we can say about it. And this mysterious spectrum is obtained by taking the zeros of the Riemann zeta function and plotting them like you would do with a spectrum. So you obtain something which is very peculiar, something which has some regularities and so on. It starts around 14, and when you look at it really in the complex plane, in the complex domain, it looks like that. So first of all, it looks symmetrical with respect to the real axis. It looks like it starts around 14, yes, and it looks like they all should be on the critical line, but we don't know. Now, what happened was that, if you want, this Riemann zeta function popped up in the noncommutative geometric framework, and it popped up for a very interesting reason. I mean, it popped up because as a special case of the thermodynamics of noncommutative spaces. I mean, noncommutative spaces have the amazing property that they have a God-given time evolution. I mean, this is what I showed in my thesis, I mean, after the work, of course, of Tobita and Takazaki, but what I showed in my thesis is that the one-parameter evolution, which was coming from states, was in fact independent of the choice of a state when you look at it modulo inner automorphisms. And that this, of course, gave immediately a slew of invariants for factors and allowed me to reduce type 3 factor to type 2 endomorphisms, except for one case which was later solved by Takazaki. But what I discovered at that time was, in fact, foliations were giving wonderful examples of, I mean, of this non-commutative space, I mean, which were in the measure theory context were factors. But the example which sort of unveiled, if you want, the role of the Riemann zeta function, came from discrete groups. Now, when you take a discrete group, when you take its regular representation, it generates a factor. So I should say one word about factors. I mean, what von Neumann and Murray did, they studied subsystems of quantum systems, and they found out that they are not all coming from, like you split the Hilbert space into a tensor square, and you look at the operators which only act on one of the two. But there are other factorizations. They are called factors, and at first most interesting ones were factor of type 2, 1, and they come from discrete group representations. But it turns out that when you extend your mental framework a bit and replace discrete group by pairs, where you have not only just a discrete group, but you have a subgroup which is almost normal. And you really think about the quotient of the larger group by the subgroup, which is almost normal, then you get type 3. In general, you get type 3. And then you can do thermodynamics, because once you have a type 3, you have a canonical time evolution, and you can change the temperature of the kind of mathematical objects that you have there by using a certain condition which is invented by physicists, which is called the chemist condition. So I won't dwell too much with this, but I will give you what it gives in an example, which was crucial, which is the work which I did with Jean-Benoît Bost in the 90s. And that's what you take as a pair of groups. You take the affine group of the rational, but with A positive. So you take, okay, AX plus B, where A and B are rational numbers and A is positive. That's your group, the large group. I call it P plus of Q. And now you take a subgroup, which is just a group of integer translations. Okay. Now, this subgroup turns out to be almost normal, whatever it means. And then you can construct out of it an Ecke algebra. And this Ecke algebra gives you a space, which is called a BC system, and which you can treat thermodynamically, as I explained before. Now, first of all, as a quantum system, it exhibits a phase transition with spontaneous symmetry breaking. So what does it mean? It means that the equilibrium states, which are called KMS states, at inverse temperature beta, they turn out to be unique when the temperature is high enough, namely the beta is less than 1, less or equal to 1. But when beta crosses 1, there is a phase transition with spontaneous symmetry breaking. You know very much what happens in a ferromagnet. When you cool it down, all the magnets will align in some direction. So it's the same, except that the directions of the magnets are replaced by a certain mathematical object, which is called the Shimura variety, which is very simple, but which is amazing because it relates the Galois theory of symmetries with, if you want, the symmetries that come from the quantum theory. So the symmetries that come from the quantum theory, they come from the group GL1 of the hat, which is a kind of adelic nature. The hat is the profile completion of the. And when you take the zero temperature states and you evaluate them on natural subalgebra, which is defined over Z, what you found are algebraic numbers. And these algebraic numbers generate the maximal abelian extension, which is called the cyclotomic extension of the rational numbers. You know, the famous Kronecker theorem that tells you that any abelian extension of Q can be resolved by roots of unity. So that's what you get. And I mean, the symmetry breaking of the physics, which is an abstract concept of beauty, actually is tied up in this example with the Galois ambiguity, which is the Galois ambiguity of the Galois extension, which is a cyclotomic extension. So already this is quite amazing. But what is more amazing, of course, than what you obtain by relating the two symmetry group is an isomorphism of groups, and this isomorphism is actually the class field theory isomorphism in this instance. So it gives, if you want, this relation, this quantum statistical mechanical interpretation of the explicit class field theory of the rational numbers. But what is much more amazing is that when you compute what is called the partition function of this system, you find that it is the Riemann zeta function. So you find zeta of beta. Now, long time ago, I was invited in '96 at the birthday of Selberg because of this work that I had done with both. And I mean, when I came back, I was haunted by the fact of really finding a relation, not only just with a zeta function appearing as a partition function, but really with its zeros. And this came about very naturally because it gave, if you want, the BC system was giving a space, and now this space has a dual in the sense of the duality between type 3 and type 2. And this dual, when you look at the scaling action on this dual, was giving you a natural interpretation of the zeros of zeta as an absorption spectrum. Now, it was also giving, if you want, the space. So the space that was coming out was of adelic nature. And as a space, it is, if you want, a double quotient. So you take the adels of Q, whatever they mean. I mean, what they are, the adels of Q, is they are putting together all ways of completing Q into a local field. And you divide them on one side by Q cross, and on the other side by the units of the profile completion of Z, which is a piece of the adels, in fact. So that's what you do. You get a space. And I mean, so I was pleased, of course, to have found this spectral interpretation, much more by the fact that it was giving an interpretation of the explicit formulas of Riemann and Weil. I will come back to that later. But it remained, if you want, as a difficult non-commutative space coming from the BC system, which is so beautiful from its relation to quantum mechanics, but it remained, if you want, as a non-commutative space, very much like a leaf space, a very difficult space to handle. And I mean, in 2014, with Katia Consani, we really made a discovery that was amazing, which is that, in fact, this space, the previous space, okay, so this space, which is this double quotient, in fact, it appears as being the space of points of a topos. So you might be you don't know what is the topos. It's a notion which is invented or discovered by Grothendieck in his work in algebraic geometry. And when I was talking about the paradigm of algebraic geometry, I mean, this is, if you want, like the most general base that you can take. I mean, it's a topos. Now, what the topos is, I mean, it's if you want the idea that somehow instead of looking at a space per se, it is not the right thing to do. The right thing to do is to do set theory parameterized by the space at which you look. And somehow the space is behind the corner. It's not there. You are just doing set theory with parameters. Now, if you take this idea and you push it far, you find out that, of course, you can take parameters to be in an ordinary topological space. But if you take the idea correctly, it extends the idea of topological space. And it extends this idea in such a way which is very similar to noncompetitive geometry. That you can take a space and you can cross it by endomorphisms, you can cross it by motions. Exactly like, you know, this matrices of Eisenberg, where just a set of points, but which are related to each other by some motion. And in particular, you can take what we call the scaling side, which is the cross product, if you want, as a topos, of the half line, 0 infinity, which you can think as the line of frequencies. And you cross it by multiplication by integers, which of course have meaning for frequencies. So you get a certain space, now a certain topos. Now, the amazing fact, which is not easy to prove, I mean, it requires some proof, is that when you compute the points of these topos, they form exactly the previous space which had been coming from the BC system and which was encoding this spectral realization. So, okay, what was very surprising is that we didn't get this just in one stroke. I mean, it happened because we had discovered before something which we call the arithmetic side, which was even much simpler, which was just the integers acting on a point, but the positive integers under multiplication. So it's not a group; it's a semi-group, if you want. It's a monoid, and you can endow these integers acting on a point with a structure sheaf. Which will be something which will have like a Frobenius for each integer. And I mean, a very simple thing which has a Frobenius for each integer is something of tropical nature, which is called Zmax. So we had discovered this object. And then what we discovered is that when you extend scalars by changing, if you want, the basic scalars, which are in characteristic 1, from Zmax to Rmax, which is very familiar in tropical geometry, then you find the scaling side. Now, the beauty is that the scaling action, which was crucial in the spectral realization before, actually becomes the action of the automorphism group, which plays the role of the Frobenius of this R plus max, and which is the elevation to the power lambda. So instead of taking an element and raising it to power, a power of p when you take a finite field, here you raise it to a real power, x to the power lambda. Lambda is positive, and you get that the automorphism group of this semi-field, which is called R plus max, is in fact given by all these analogues of Frobenius. And when you let these analogues of Frobenius act on the points of this topos, you find exactly the scaling action that was used to get the spectral realization. So one has a perfect analog, of the framework of the finite fields. And moreover, what we proved with Katia Konsani is that there is all the more, a perfect analog of the Hasse-Weil formula using fixed points for the Riemann zeta function. And this is very subtle because one has to let the Q of the finite field tend to 1. And also the counting function is no longer a function, it's a distribution in the sense of Schwarz. So, I mean, there are all these points. And of course, I mean, all these points, they give you some confidence that it should be possible using the structure, to go further. So what we found is that the structure sheaf of this scaling side, which gives, if you want, the geometric structure, because as I said from the start, I mean, when you do algebraic geometry, just a topos is not enough. You need to have a structure sheaf. So the structure sheaf is of tropical nature. It is a sheaf of piecewise affine convex function with integral slopes. So, I mean, you have this now, you have this structure. And what you would like to do is to use the idea of Matuk-Tate and Grothendieck. You see, when Weil proved the great fact, which is the analog of the Riemann hypothesis for function fields, his proof was kind of tricky still. And it was extremely conceptually simplified by Matuk-Tate and Grothendieck, because Grothendieck gave the final shot, if you want. And the idea that they had was that, when you want to prove the analog of the Riemann hypothesis, you have to prove that some quadratic form is positive. Okay, I simplify over, but that's what you need to prove. And in order to prove that, what they did, they crossed the space with itself, then you get a surface because they are dealing with a curve. And then they, on this surface, they applied the Riemann-Roch formula. And the Riemann-Roch formula immediately implied the positivity that they wanted when you were using the Riemann-Roch for something which was related to these graphs of the Frobenius, if you want, to this combination of graphs. Okay, so I mean, with Katia, of course, we wanted to do something like that, but what happens when you try to do that, if you want, is that you have a difficulty, and the main difficulty, we will see immediately why, is the subtlety of the local terms in the explicit formulas of Riemann and Weil, as I will show you immediately. And so what we did, instead of trying purely geometrically, I mean, it couldn't be done totally geometrically because of the subtlety of these terms in the explicit formulas. So what we did was to relate our framework of geometry to the analytic framework by using the Schwarz kernel. So this is what I explain now. And I mean, if you want the analog of Weil positivity that you need for the Riemann zeta function itself, is following. You write the explicit formulas of Weil. So I mean, it's a formula which, I mean, Riemann Weil, because I'm sure, I mean, Riemann would not have been surprised at all by this formula, because he applied it, in fact, in many cases. So, I mean, this formula gives you the sum of the values of the Fourier transform of the function on zeros of the zeta function, non-trivial zeros, and it equates this with the sum over what are called places of the global field Q of rational numbers. Now, you will see when I write so I mean, the Riemann hypothesis is equivalent to the positivity. Why there is a minus sign? There is a minus sign because you see that there is a minus sign in front of the zeros, so you have to put an overall minus sign to get this positivity. And I mean, when I show you the formula for the contribution of the Archimedean place, you will be a little bit frightened because, it's weird. I mean, when you see this formula for the first time, you think, wow, how am I going to prove, positivity by using such a formula? So, I mean, the formulas for the contribution of the other places, the primes, are much simpler. But the formula for the Archimedean place is quite tricky because it takes the principal values. It's something which is divergent because of the x minus x inverse in the denominator. It diverges at 1, and you remove the divergence in a certain way, which has to be very, very, very carefully defined. I mean, it's not at all arbitrary. I mean, this is the principal value. So, in fact, there would have been no way to attack this problem without having, of course, a better understanding of these local terms. But this better understanding is what I had obtained when I wrote my paper in Selecta Mathematica in 1998. And it's the semi-local trace formula. And what it does, if you want it, instead of taking all the places at once, it takes a finite number of places containing the Archimedean place. And it replaces the Adels, or the space we were talking about before, by a much simpler space, which is the product of the local fields over a finitely many primes, plus the Archimedean prime. And then it turns out that the complicated local terms of the Riemann-Weil formula, they pop up. And they pop up very, very simply by a formula which uses the quantized calculus, which I was mentioning before in the case of space-time, and which is that what you have a certain unitary operator which is intimately tied up to Fourier transform. And when you take its logarithmic differential in the quantum sense, you put a 1/2 in front. So this 1/2 of u star, this slash u is this logarithmic derivative. Then when you take the trace, you find that it is the sum of the precise principal values defined by Weil over the finite set of places for the test function h. So, I mean, of course, this means that there is a way to handle, there is a way to comprehend these local terms and to relate that to the geometric part that I was mentioning before. What we did with Katia we considered, if you want, the association between these operators and their Schwarz kernels. I mean, when you have an operator in a space, the Schwarz kernel will be an operator in the square of the space. So this corresponds exactly to the Matuc-Tate idea of taking the square of the curve. And moreover, the operator being scaling, it corresponds exactly to the graph of the Frobenius. And when you do that, you find that this distribution, which looked very, very complicated, in fact, because of the expression for the quantized calculus, splits out into a sum of two pieces. There is one large piece, which is called sigma, and there is a small piece, which is called delta. And when you look at these pieces, you find out that they give you one idea. They give you the idea that while this spectral realization, which I had done a long time ago, was by an absorption spectrum, when you look at this geometric picture and the Schwarz kernel and so on and so forth, you find out that no, I mean, in fact, there should be a way to replace this absorption spectrum by an emission spectrum. Remember that, it was just for a small break, that it was an amazing fact that at the end of the 19th century, while the physicists had invented a new chemical element, which they had called helium, and they had invented it, I mean, physicists and chemists, because of the spectral lines which were unexplained and were coming from the sun. Then there was an eruption of the Vesuvio, and spectral analysis was done of the lava, which was exiting from the volcano. And boom, they found that there was an emission spectrum, which was helium. So helium was discovered on Earth. So, I mean, here we are in a similar situation, and we want, of course, you see, the big trouble with the absorption spectrum is that it doesn't allow you to prove positivity or something like that, because it's kind of measure zero in a continuum. So the emission spectrum is much better. And in fact, I mean, I had been for a long time puzzled by an idea of John Keating and Michael Berry. I mean, they had the idea that they were doing something very strange compared to what I was doing. They were using the same operator, which is a scaling operator. But instead of making a cutoff and looking at it as an absorption spectrum, they were looking at it in a very strange way, which I was very dubious about, which was to impose a cutoff, in these two ways, which was totally artificial, but they were getting the right semi-classical limit. And at some point, I had made the computation that, in fact, there was an explanation for what they were doing, which was that I could take my own interpretation as an absorption spectrum, but I could subtract this interpretation from the white light. And when you do that, you find exactly their picture, but you also find exactly the picture which we had found with Katia, which is here. So, I mean, all these things were, quite enticing. And what we did with Katia was to treat the simplest possible case, which is the case of the Archimedean place, and take this seriously, take the computation we had done with the Schwarz kernel correctly, and then what we found is that there was an abstract reason for positivity. The abstract reason for positivity is a very simple lemma. In fact, I mean, it was also motivated by an attempt which had been done by Xianjin Li for our age. And this positivity lemma is amazingly simple. What it tells you is that it's in the framework of the quantized calculus, but it tells you that automatically, if the unitary that I was talking about before, which is related to Fourier, would be triangular in the decomposition corresponding to the quantized calculus, then you would immediately have that -1/2 of trace of f u star f u would be positive. Why? Because it would be equal to the trace of the product of the function f, which, is positive, by the projection on what will play the role of the sun in space, which I call S for this reason. But it's a general lemma. It's a general lemma. So it turns out that, in reality, the triangularity of the operator is not true, but one can compute the discrepancy. And what one finds is that this operator is not triangular, this unitary is not triangular, but it's triangular modulo infinitesimals in the sense of the quantized calculus. So because of that, you can compute the difference and you can correct by the difference. And then when you correct by the difference, you can try with a computer to see if you get the positivity that you need. And amazingly, so this is the discrepancy, the graph of the discrepancy. You compute its Fourier transform, put it on the computer, and amazingly, you find that it gives you something positive. Now, of course, you have a conceptual reason for this positivity coming from operators and so on. And when you look at it very close, of course, you can be scared, because it's never a proof. The computer can draw a graph, but okay, how can you say, that the thing is positive? You need a proof. So the proof is conceptual. But what is truly amazing is that this compensation of the derivative of the Riemann-Siegel angular function is in fact almost exact. Namely, the Riemann-Siegel angular function is not positive. It has a drop, if you want. It has a piece, the derivative of it, which is negative. Which is that the function is not increasing. It has a place where it's not increasing. And discarding this place was a mistake done by Xanjin. But the correction exactly compensates for that. So in fact, with Katia, we went further, and we went further by, if you want, really doing the analysis of the discrepancy of this discrepancy using pairs of projections and so on. And what we found is using pairs of projections, as I had defined them in my paper in Selecta. What we found is the following theorem. We found that the veil term, which one would like to prove to be positive, is, which I call here W infinity of f in the formula, which is minus the WR, can be expressed as a trace of the action if you want, the trace of the product of the function by the projection on Sony space. But the function doesn't restrict to Sony space. Multiplication doesn't restrict, but you can take their product. And of course, the trace of a product of two positive operators is positive. And so this is the root of the positivity. And it is exactly the root that I was talking about before, namely this root about triangular unitaries. But there is a remainder. There is a remainder, but this remainder is perfectly computable, and it's computable in terms of prolate functions. And we analyze this remainder, and what we proved, if you want, what we proved is that in fact this remainder doesn't spoil things because it has the correct sign. So in other words, the veil functional, which is minus WR, okay, and which is the one you want to be positive, is in fact larger than the trace of the product, if you want, of the scaling action by the projection on Sony space. Of course, when you have a square, you can move things using the trace property. So this is what we have, and this was published recently, in Selecta Mathematica as a kind of echo of my '98 paper. But it was not easy, because the referee didn't understand anything in the paper. Okay, so now with Katia, in fact, this year, what we did was to analyze the. I should have said before that one reason why this work for the Archimedean place is very meaningful is that in fact somehow the process and the most important fact is that this unitary, which is coming from the semi-local trace formula, is not triangular, but it is almost triangular in the sense that the piece which is not triangular is an infinitesimal. Now, what we also proved that last year with Katia is that, in fact, the same properties that the piece which is bad is infinitesimal continues to hold when you take finitely many places. Now, this fact is extremely promising, and probably this is what finally convinced the editors of Selecta to accept the paper. This fact is extremely promising. Why? Because it says that there should be a way to extend our result to finitely many places. Now, if you do that, you are finished because you prove the very positivity. Okay, so I mean, in fact, with Katia, what we did this year, in the meantime, was to understand the infrared behavior, if you want, or the low-lying zeros of the Riemann zeta function. And I mean, the way we did it was to again use these prolate functions that were so efficient before. And we used them to define a spectral triple, namely a non-commutative geometry, which is obtained by, if you want, conditioning the most trivial thing, which is the Dirac operator on a circle, by these prolate functions. And I mean, I gave a very detailed talk about this in June of this year, 2021. And so I won't repeat this talk, but I will just show you a few pictures, I mean, to give you what was going on. So, I mean, what was going on is that what we did, we took the periodic Dirac and we perturbed it using this projection on the... what I didn't know when I gave my talk, in fact, is that the part of the spectrum on which we get old, it comes from fact that we cut in the sum over integers. I mean, like in the Riemann zeta function, we cut it to some level. And the reason why we cut it to some level is that when we take this prolate projection by which we perturb the Dirac Pareto, in fact, the sums which are involved, the sum of f of nx, because of the support of the functions, they only involve a few n. Now, what we found out with Katia afterwards, I mean, after I gave the talk, is that in fact the cut at which n we stop is exactly the same as in a very famous unpublished formula of Riemann, which is the Riemann-Siegel formula. And I mean, when we did the calculation, so when we did the calculation, we got this spectral triple, which was depending on lambda. This is so it's like we are an experimenter, and we are allowed to choose the frequency at which we work, the lambda at which we work. Okay, and what we had found with Katia is that it was we were getting spectra of these Dirac operators perturbed, which were really looking like the low-lying zeros of zeta. I mean, amazingly similar. But I mean, they were never thought, okay, I mean, which lambda do you choose? Now, but what we discovered is that, in fact, the lambdas which are meaningful are those in which the various choices for making the cut, if you want, coincide. And when they coincide, the value that you get is exactly right. So, for instance, for the first zero of zeta, I showed this type of graphics, and they were showing that, when the ways of doing the cut agree, that you get exactly the right eigenvalue, which is the corresponding zero of zeta. And from that, we developed with Katia, I mean, the criterion and so on. And from that, we were able to compute without mentioning zeta, without mentioning analytic continuation whatsoever, just operators. So we were able to compute, if you want, the first 31 values of the Riemann zeta function and compare the two spectra. And there is no difference. I even forgot which one is coming from zero of zeta and the one which is coming from our way of spectrally understanding what is going on at the infrared level. So, I mean, time is running, of course. I don't want to spend too much time, but still, I want to mention that somehow, at this point where you see this spectral coincidence and so on, you could say, well, okay, now forget about the geometric aspect and so on. No, I mean, it's behind the scene. And what we found with Katia is that, in fact, we understood that when there was coincidence, there was something going on which we call zeta cycles. And it turned out that with these zeta cycles alone, you were not able really to give a spectral realization. But in order to give the spectral realization, you have to put them together. And amazingly, the space of parameters, which allows you to put all these things together, is a scaling side. And I mean, how does it appear, the scaling side? It appears because these zeta cycles have the same algebraic property as geodesic. Because if you take a geodesic, you can turn it around several times. So you have a way, if you want to cover it by n times. And this gives you a kind of action of n cross. Now, for the same holds true for zeta cycles. And I mean, it gives you, in fact, that these zeta cycles, the correct parameter space is a scaling side. And so what we did with Katia, which is not yet published, is that we proved, in fact, that the spectral realization on critical zeros, very important, is in fact obtained as an H1. I mean, it is in fact I mean, it's what you have to do is you have to take on this scaling side X, you have to take a sheaf, and this sheaf is best described in terms of a theory which I don't have time to talk about, which is a theory of S algebras, and I mean, which is a theory, if you want, which cures two difficulties with spec Z. One is that Z times Z is Z, but I mean, when you take the correct base, which is in fact going back to Waldhausen and Goodwillie and so on, which is related to the sphere spectrum, in the guise defined by Graham-Siegel, then you cure this difficulty, but you also cure several of them. You cure the fact, for instance, that now you have a structure shift for the Arithmetic compactification, whose torque at infinity is related to the Gromov norm. So I won't involve on that because I want to finish on something which is really new, okay, with respect to all types of previous work, and which is a collaboration with my collaborator of a long, long time, Henri Moscovici. And I mean, what we have done with Henri, we have done it, we have stumbled on something by accident. I mean, there is no other description. And what we have solved as a problem is a problem which was really there for a very, very long time, which is what about the ultraviolet behavior of the zeros of theta? You see, what I have described with Katia is the infrared behavior. So it doesn't say how the zeros behave when you go very, very far out in the spectrum. And as a model that we had with the Dirac operator, which is periodic, of course, doesn't answer this question, because when you take the perturbed Dirac, after a while, the zeros will be the same. I mean, as for the Dirac, so they will be just, you know, very, very easy behavior. The zeros of zeta have a very complicated behavior. Why? Because when you look at the number of zeros, which was computed by Riemann, what you find is that the number of zeros of zeta which are less than E, where E is some number, positive number, I mean the zeros which are positive imaginary part, which are less than E in imaginary part, what you find is that it's E over 2 pi times log of E over 2 pi minus 1. This is very strange, because if you take a manifold of dimension 1, and if you look at its spectrum, you know, of course, you'd like to find the zeros of zeta as coming from a Dirac operator on a one-dimensional manifold. Well, it never gives you that. I mean, it gives you something which is like E proportional to E. And this E times log E, you know, I mean, when you think of it in terms of what we call the dimension spectrum with Henri, I mean, it gives you a dimension spectrum which is weird, I mean, which has a double pole at the point 1 and so on. So it looks like an impossible problem. But I mean, with Henri, we stumbled, I can say we stumbled on the solution of this problem. Okay. And it turns out that what we found is a natural Dirac operator, which is in fact intimately connected with Sonin space. I mean, I am not able to tell you too much because it's a kind of embargo on this idea. So it's intimately connected with solid space, and it has exactly the correct ultraviolet behavior. And from the principles of non-commutative geometry, we are gradually unveiling the corresponding geometry. It's very, very interesting, very mysterious geometry, but which is given to us, handed to us by the operator. We stumbled on the operator, and then we are unveiling the geometry. And what is extremely interesting, and I want to finish on that, is when you compare the spectrum of this operator, which we know to be on the critical line. I mean, it's not that we restrict zeros to whatever. No, we know this full spectrum. When we compare it with the zeros of theta, here is what we get. So I will show you some comparison. So here is a comparison at the infrared level. Okay, so there is some obvious difference. I mean, because you are at the infrared level. And then, you keep going, you keep going, you keep going. And so you can see there are yellow dots and there are blue dots. And the yellow dots are our spectrum and the blue dots are the zeros of the Riemann zeta function. And it continues like that. I mean, it continues like that. I mean, of course, the Riemann zeta function is a little bit more erratic than the other one. But I mean, their ultraviolet behavior, their behavior at infinity is exactly the same. It's exactly right. And this we know for our operator. So if we want, what we have done with Ari is we have really stumbled on a geometric space handed to us by an operator. This operator has the right spectrum. It's not yet the right one. It's not yet the right one because, if you want, in a sense, it is related to the Archimedean place alone. It doesn't yet, if you want, contain the input from the prime numbers. And it seems clear to me that this input from the prime numbers will come from the semi-local framework that I explained before. Okay, so this is where I will end up. And so what happens really is that, these two types of spectra or zeros, they interlace, namely one is between the next one and the next one is between the two with the same end. I mean, this is really an amazing fact. Okay, so I think I will end up here, and I will have conveyed the idea that, there is this spectral standpoint which will require a lot more work, but which is really the way many things actually manifest themselves to us for our understanding. Okay, thank you. I will finish here.
Thank you very much, Alain.
Yes. Okay.
A wonderful talk. Yes. Are there any questions or comments?
Yeah, I should have said one thing at the end, which is that when you see only a yellow dot, this yellow dot is hiding the blue dot which is behind it. So I mean, when you only see a yellow dot, it means that they are really the same, or essentially the same. I mean, this is important to say.
Yes. Okay. So yes, please go on with questions, comments. Maybe I start myself. I've been a bit selfish here, so sorry. So for quantum gravity, what do you think? What modifications of the spectral paradigm you think is needed, or you don't think is needed? I mean, I want an answer which would be very philosophical and kind of looking. I mean.
Yeah, sure. No, I think if you want for that, okay, this would require a whole talk somehow. So, I mean, what we have found with Ali and Walter is that the spectral action was sort of natural when you take second quantized fermions. And what happens is that when you take second quantized fermions, you can recast the spectral triple in the second quantized level. In other words, what you have to replace the Hilbert space by the Clifford algebra, infinite dimensional, and you have to replace the Dirac operator by automorphisms, which are corresponding to the Dirac operator. What the algebra has to be replaced by, we don't know. But what is clear, if you want, is that the step which is waiting be done is to blend together. Somehow, if you want, the point of view of spectral triples is very much like a first quantized point of view. And so what remains to be understood is to which extent one can incorporate the quantum corrections and so on, but this will require to go to the second quantized level. So if you want, there is a general principle which I have observed many times, which is that somehow, you know, the theory, operator algebras and so on, they are like the second quantized form of Hilbert space. And there are many reasons to advocate for that. So I mean, this seems to be a natural trail. And one other reason why I think it's a very natural trail is the following: is that somehow, you know, spectral triples are of course intimately related to cohomology for the sort of homotopical information that they contain. Now, it turns out that it's natural to think that when you go to the second quantized level, you should get a theory which is naturally dual to algebraic K theory, to the algebraic K theory of Quillen. So in other words, I mean, you know, at the homological level, even at that homological level, there is a natural question which arises, and which is to understand what replaces K homology at this level. Now, okay, and there are, of course, you know, plenty of questions, and what one has to do is to experiment with them. I mean, one other thing which is very surprising in the work that we are doing with Henri is that we have to extend spectral triple a bit, because we have a space which is a little bit like space-time. I mean, it has an imaginary time. So I mean, this says that, you know, the research that that is done partially. I mean, I know that there are very good contributions already on that topic of replacing spectral triple in order to deal directly with space-time, not with the Wick-rotated space-time. So I mean, this type of thing is also going to play a key role, I think. So I mean, if you want, the idea of spectral triple is quite basic. I mean, it is a paradigm of geometry which obviously allows a lot of things, but okay, I mean, you know, to say that it is a final paradigm would be stupid. I mean, it has to be experimented with, it has to be used, and so on and so forth. And
you meant, you meant Lorentzian spectral.
I meant Lorentzian, exactly. I meant Lorentzian signature. So what happens in the work with Henri is that very surprisingly, I mean, this is extremely surprising. Not only we find something which is related to the zeros of zeta, but the part which is sort of imaginary, I mean, or if you want, Lorentz gives you the trivial zeros of zeta, which is mind-blowing somehow. And we cannot say that we really understand what is going on. I mean, you know, so this is the situation. I mean, and it's kind of the situation which I love in mathematics, namely the situation in which instead of, you know, you are looking for something and you can write a proposal and you say, oh, okay, in 1 year I will have done this and I will have. No, I mean, come on, this is not what we are doing. I mean, you are looking for something for understanding and you find something else. I mean, you find something totally unexpected. So that's exactly what happened to us. I mean, you know,
yes.
Exactly what happened to us.
Yes. Thank you. Any other comments or questions from the audience?
I think
I have a
yes.
I have a question.
Yeah.
Yes. So, is it possible to classify all representation of the two-sided equation?
That's a pretty good question. No, I think if you want, I can tell you what one should expect, but with an enormous work. If you want, one should of course impose a few conditions on the representation. One of the conditions should be, if you want, that the Weil growth for the Dirac should be like in dimension 4.
Ah, okay, okay.
So what I know is that if you do that, then the volume is quantized. This I know. Moreover, so a certain number of things are already there, but one would have to prove a fantastic generalization of the reconstruction theorem in order to answer your question. You see what I mean? So I mean,
so it would be difficult, yes.
Satisfactory. What is very satisfactory is the following: is that you see, when people saw the Eisenberg commutation relations, they extended them. How? How did they extend them? They extended them by Lie group representations. And then there was the Harish-Chandra theory, you know, all the physicists, and of course, I mean, you know, with amazing work, Wigner and so on, Bergman and so on. But by doing that, if you want, you cannot, of course, expect to get geometries by doing that. I mean, you will get a few parameters, but you won't get, you know, that the representations themselves are geometries. And that's the big input of the higher Heisenberg relation. The big input that what we know already is that among the representations, you will have those which come from spin-4 manifolds. We don't know what they are all. Okay, what should be expected is that you get something like singular manifolds and so on. But if you want, the main idea is that by passing from the ordinary Heisenberg relation to this higher Heisenberg relation, then, oh, wow, you find that geometry is born in Hilbert space framework. So it's born in quantum mechanics. And that, I mean, that mere statement should be, of course, a very strong indication for people who are doing physics, because gravity is the story of geometry. But then you have to find it compatible with the quantum. And that's already a sign, you know, that the compatibility is amazing. It's amazingly difficult because it will be, of course, very, very, very difficult to prove a theorem of this kind. But somehow, you know, already we know that at least all the manifolds give you such a representation. And what probably I didn't insist enough in my talk is to explain that what we were looking for with Ali and Slava, it was really a purely geometric problem. We had no intention to find the standard model at all. We wanted to, you know, we had already done work with Gianni and so on, where in 2000, I mean, where we were describing the sphere using a very simple thing like 2x2 matrices and a free product with a projection. So that was already very satisfactory, because what it is saying, if you want, is that there is a way to encode the algebra in a way which is almost combinatorial, because you give it like a free product. What we had with Gianni was a free product of like 2x2 matrices with a projection. When you write such a free product, you can just write words. So you are talking by words, adding them and so on, and that's your algebra. It's not the algebra of functions on the sphere, it's algebra of 2x2 matrices of functions. But it's much simpler to give like that than to give the algebra of functions. And the idea is that if you want the algebra which is used by the universe, or okay, it is of the same type. It's something which is very simple to end combinatorially, and which then, okay, because it has to be ended combinatorially, it cannot be commutative, because the commutative creates a collapse. If you apply the commutative to the language, all the anagrams are the same. So you collapse the meaning. So you collapse the information which is a priori available into a desert by passing to the commutative. The lesson which I learned, if you want, from the non-commutative is precisely that, is that in fact the non-commutative is not weird, it's not you know, strange. No, we are so used to it because we speak, because we write. So we are used to keeping the information from the order of the letters and the order of the words. And so, I mean, and this is the essence of what we are trying to do. So what we are trying to do, we are trying to write down, if you want, the four-dimensional stuff in such a way that it would be optimal from this point of view. And then we found these algebras and we were stunned. We were really stunned. But I can tell you, I mean, obviously it says that the message didn't get understood. You know, the message is there, it's boom. But, you know, might be I didn't talk enough about it, or I don't know what. But I mean, so this is, I think this is a very important thing. I mean, with respect to the question of Masoud about quantum gravity, you see, I think the quantum gravity, okay, I mean, it's a very far-fetched goal. There is the goal that we were addressing is a much simpler goal. It's to understand why on earth aren't we just living in gravity? I mean, this would be beautiful. We just have the Jimmy News and we'd all be happy about it. No, it's not like that. So one has to understand just understand. I mean, you know, why it has to be something like that. And I mean, I believe, at least for myself, okay, I found an explanation. Maybe there is something to be improved and so on and so forth. But then I lost my interest into this problem after doing that, because I had the impression that the reason was there. You know, the reason was something very combinatorial, a language as simple as possible, because of the Clifford algebra being so simple, that would actually answer the question.
Any other questions?
May I add something?
Sure.
So the dream is to somehow take an integral over all possible representations, yes?
Okay, well, that's okay. Then you see, this again is a very interesting question for the following reason, because there is, if you want, there are two approaches in quantum field theory. There is the one you mentioned, which is the Feynman integral, which is in a way the one which is most directly understandable, because you can write the integral even if we don't know what the integral means. Doesn't matter, we can write it down. Okay, that's one thing. But there is also the particle approach. And the particle approach would mean that you have these geometries and they interact with each other. You see, I mean, so it's like if what I have given you are the irreducible representation of the Poincaré group. So you have like the notion of particle, but you don't have the ways they interact. And then the way they interact, it should be also at the particle level. So of course, this remains to be done. Now, what you are asking about, you know, possible functional integral and so on, this can be and probably should be approached by taking a finite dimensional approach, and that's what we're trying to do also with Walter by considering operator systems and all that, and trying to find, if you want, an approximation to these relations in finite dimension.
Because some matrix model, yes?
Yeah, kind of, exactly, matrix model. So of course, but I mean, so you know, this one, I think one should remain quite flexible and so on, and I mean, progress will come, but I think it will come by accident. I don't think one can even write a proposal on that. I mean, you see what I mean? I mean, I think that I have really this very strong belief that if you do some work to understand, then some things will pop up, and sometimes you'll be very surprised. This is exactly the way we were in our work with Henri. I mean, you know, we were extremely surprised because we had no intention to find this ultraviolet behavior at all. I mean, you know, this was totally foreign from our intentions, but we just stumbled on it. Of course, then you have to recognize what you stumble on. I mean, and I should add one thing, which is that the use of the computer is extremely important. It's extremely important to be able to handle the computer, and then, you know, okay, I mean, you have some idea, and you can any idea, in fact, I believe, can be, you know, already tested if you know how to use a computer, really. I mean, now we have something which Riemann didn't have. I mean, you know, he didn't have that. I mean, he was computing by hand, you know, he computed a few zeros and so on, but I mean, you know, if he had the computer, I don't know. I mean, you know. Yeah.
Okay, so other questions? Come on, here's a chance to ask questions. Was everything very clear?
Sorry, I have a question.
Yes.
Yes.
Yeah.
Would you think, is it wrong to try to reproduce some transition amplitude of some simple interactions, ignoring the effect of gravity within the framework of spectral action?
Yeah, you can do that. You can do that. You can certainly do that. I mean, this is what we did when we found, if you want, that the standard model emerges and with a fixed background. So it's already done, you know, if you want. Yeah. No, this is perfectly fine. Yeah, sure.
Yes. Other comments, questions?
May I ask a final question?
Sure.
So why do you believe that the second quantization has something to do with the being dual to algebraic K-theory?
Okay,
It sounds mysterious.
Yeah, no, it's not so mysterious, because I don't know if you know things which are called the Schwinger terms.
Something related to the spin representation of?
Yeah, well, I mean, it's something which was
anomalous commutator.
Yeah,
something.
exactly. Yes. Yeah. Now it turns out that these Schwinger terms, when you think of them abstractly as a mathematician, they are related to algebraic K2. And they get an interpretation exactly from from spectral triples, but when you go a little bit to the second quantized level. So I mean, it's not totally stupid what I said. I mean, in the sense that there are some hints. On the other hand, okay, I mean, it's more like it's a little bit like telling you, okay, there are two things which are extremely complicated, maybe they are related. So I mean, it's a little bit like that. Huh? Don't take it too seriously. But on the other hand, okay, I insist on the fact that while a great discovery of Atiyah Singer, really, I mean, independently by Atiyah and by Singer, was the introduction of the abstract elliptic operators and, if you want, of the K-homology. I say independently by Atiyah and Singer because Atiyah wrote this little paper about abstract elliptic operators, but Singer also wrote a very visionary paper in 1970, in which he had similar ideas. So I mean, the fact that they discovered that the K-homology cycles are best realized in Hilbert space, which of course, then was tremendously amplified by Kasparov, by Brown-Douglas-Fillmore, by, all of these developments. This is somehow missing at the level of algebraic K-theory. So what we have, if you want to, we have algebraic K-theory of Quillen, which is very sophisticated. It's an extremely sophisticated machine in the sense that, okay, K0 and K1 are easy, but the higher Kn are extremely fancy objects. I mean, they are obviously extremely fancy objects. And the point that I want to make is that, after all, they are not based on an algebra, they are based on the GLN groups for n large. So it's not like you are using the algebra, you are using its collection of GLN groups. And that fits perfectly with the second quantized point that I wanted to make. Because on the Clifford algebra, you could act by this group, not by the algebra. You see what I mean?
Yes.
You see what I mean? So I mean, there are several hints. And there is certainly a missing theory, which is dual to algebraic K-theory. I mean, the enormous advantage when you have a theory and it's dual is that you have pairings, and you can decide that some cocycle is non-trivial because it pairs non-trivially with something else. So I mean, it's, what one can say, I would summarize, if you want, saying by saying that, okay, we understand more or less the first quantized level, but I believe that, okay, we need to go further.
Okay.
Okay, thank you very much.
Thanks. Any other questions, or we are now abusing Alain? So
I'm perfectly rested. I didn't talk.
I was.
It was my alter ego who was talking.
Yes. Any other questions or comments? Okay, so I'm sure there are a lot of questions to be asked, but well, in time we will ask them anyhow. So if there are no more questions, I don't see anything in the chat anymore. If there are no more questions or comments, let's thank Alain for fantastic and inspirational talk. Yeah.
Thank you, Alain.